You ready? All right, today we're going to talk about comparators. This is basically applications of op-amps. Now the first one you're going to look at is a comparator. What does a comparator do? A comparator compare voltages. All right, that's what a comparator do. Now the first one we're going to look at, they talk about a zero level detector. We're going to look at the zero level detector. Why they call it a zero level detector? We're going to detect our reference, in this case is 0, and we're going to compare the input signal with 0. There's my input signal. Now you will notice my reference here is 0. And let's have a look what's happening. If my input signal passes 0, when it goes positive with respect to my reference. And what input do we need? You use here, we use a non-inverting input. That means when it goes positive, it will shoot up maximum positive and stay positive for that whole duration of time. At this point, my input signal becomes negative with respect to my reference. When it goes negative, it will shoot down negative to maximum V out. What determines the maximum V out? The supply on the op-amp. That means the op-amp's output can never go higher than its supply. Normally a little bit lower than its supply, but that will be determined by my supply. That's why they talk about plus V out max and minus V out max. You notice there's no feedback here. That means this thing will always go to the maximum values, positive and negative. In the next, we're going to talk about non-zero level detectors. In this case, if we have a look, here I got a positive voltage reference at my inverting input, and I'm going to compare that with my sine wave. Now my reference voltage there is positive. Now let's have a look. Here my input signal is 0 and my reference is positive. But where is my reference positive? At my inverting input. That means I'm going to invert positive. That's why I will be maximum negative, also determined by my supply of my op-amp. But now my input signal increase. At that point, what happens? Input signal becomes more positive than my reference. When it becomes more positive, what happens? Then it will shoot up positive, all right, because that is now more positive and will stay positive for that duration of time. What happens here? It becomes more negative. When it becomes more negative, it will shoot down negative and stay negative for this duration of time. Then it becomes more positive again, will shoot up positive and stay positive. Here, the same circuit, but here we got a voltage divider for my reference. Here I got a Zener diode for my reference. All right, that's why they call it a non-zero level detector. All right, let's have a look at example 13.1. They say the input signal in figure 13.3a is applied to a comparator in figure 13.3b. Draw the output, show the proper relationship to the input signal. Assume that the maximum output levels of the comparators are plus minus 14 volts. That means the maximum output can go to plus minus 14 volts, all right? Here's my input signal, positive 5 volt, negative 5 volt. I got a voltage divider here. I must determine the voltage there. That means that resistance on top plus that at the bottom times 15. V reference R2 over R1 plus R2 times plus V, and that's 15 volts. Work that out, I'll get a reference voltage of 1,63 volts. That means the voltage at that point is equal to 1,63 volts, all right? Now here is my input signal. There's my reference voltage. My reference voltage is at my inverting input. Now if I look there, what is my input signal there? My input signal is 0. My reference is positive. That means the output will be negative. At that point, my input signal becomes more positive than 1,63 volts, it will shoot up positive and stay positive for that duration of time. Stay positive. Here my input signal becomes negative respect to my reference. It will shoot down negative and stay negative for that duration of time. And there again, it becomes more positive, shoot up positive. All right, now we're going to look at the effects of input noise on comparator operation. All right, here I got a sine wave, but superimposed on this sine wave is noise. But we know the comparator will work like this. When my input signal goes through 0, because my reference here is 0, it's going to detect this input or compare this input with 0 volts. Now each time that thing goes through 0, it will change state. Now let's have a look at this. Now let me just move it up a little bit. If I look at this, there my input signal goes positive with respect to my reference. What will happen? Then it will shoot up positive. There it goes negative with respect to my reference, it will shoot down negative. That means if you look at this, there I will get a few trigger points, there I will get a few trigger points, and there I will get a few trigger points. And that is due to the noise. And we want to reduce that effects. And what do we do when we reduce that effects? We're going to make use of hysteresis. What is hysteresis? Now, hysteresis will give me positive feedback. That means here's a circuit with hysteresis. That means that's my non-inverting input, and I take it there. That means that is positive feedback. That is not negative feedback. And that will give me two trigger points, an upper trigger point and a lower trigger point. That means if my output is positive, what will I feed back there? I will feed back positive there. If my output is negative, what will I feed back there? I will feed back negative. That means then I will, if the output is positive, I will compare the input signal with this positive voltage, and where the output is negative, I will compare the input signal with a negative voltage. Right, let's quickly have a look here. Now they show us the output is maximum positive. That means I'm feeding back a positive voltage. That means that is my upper trigger point. When that signal, that sine wave, we go higher than that, what happens then? Then the output will shoot down negative. Let's have a look here. There's my upper trigger point. The output is positive because I'm feeding back a positive value. Now, as this signal increases, at that point, what happens? The input signal becomes more positive than my upper trigger point. What happens? The output will shoot down negative. All right, but now this voltage here is going to be negative. All right, and that will show me my lower trigger point. That means when this signal goes lower than the lower trigger point value, at that point, what will happen? The output voltage will switch up positive. And that is called hysteresis. That gives me the hysteresis. There's the formula. Upper trigger point R2 R1 plus R2 times plus V out maximum. And for my lower trigger point is equal to R2 over R1 plus R2 times minus V out maximum. The hysteresis value is the difference between the upper trigger point minus the lower trigger point. Let's have a look at this example. They say determine the upper and lower trigger points for the comparator circuit in figure 13.9. Assume that plus V out max is plus 5 and minus V out max is minus 5. All right? Upper trigger point R2 over R1 plus R2 times that, and that will give me 2.5 volts because R1 and R2 got the same value. That's why it will give me 0.5. And for the lower trigger point, minus 2.5 volts. Then we're going to look at output bounding. Now, up till now, we know that the voltage will always go to the maximum values, all right? And that will normally be determined by the supply of the op-amp. But now if we want to limit that output to a certain value, we can make use of output bounding. And what is output bounding? And now it's done. All right. All right, what we do with output bounding, we put a Zener diode in the output of that comparator. There we put a Zener diode there at the output of the comparator, and let's go and have a look how these circuits are operating. I'm going to explain each one to you, or try to explain each one to you. All right, let's assume, what is my reference here? My reference here is basically 0 volts. That means I'm going to compare this input signal with 0 volts. If this input signal goes positive, what will happen? That is the inverting input. The output will go negative, all right? But negative to what value? That means now I'll have 0 volts here. I will have a negative voltage there. That means this Zener diode is forward biased. It will act like a normal diode. There's 0 volts. That's why it will go to minus 0.7. Now, when my input signal goes negative with respect to my reference, where will the output go? The output will go positive. That means there's 0 volts, output go positive. Now what happens now? Now the Zener diode is reverse biased, like it should work as a Zener diode. That means if it's a 5 volt Zener diode, that thing will go to the Zener voltage, and that's 5 volts, and stay there for that duration of time. When the input signal goes positive again, it will go again to minus 0.7. That is bounded as a positive value. The next one, we turn the Zener diode around. Now they say bounded as a negative value. Again, if my input signal goes positive with respect to this reference value, what will happen? The output will go negative. All right, there's 0 volts, it goes negative. What can I say about the Zener diode? There's 0. How does current flow? Flow from positive to negative. The Zener diode is reverse biased. It will go to minus VZ, all right? Now at this point, what happens? My input signal goes negative with respect to my reference. Where will the output go? It will go positive. There's 0, it goes positive. The Zener diode is forward biased. That's why it will go to plus 0.7 volts. In the last case, let's have a look here. We've got two Zener diodes back to back and exactly the same circuit. There's my reference. When my input signal goes positive with respect to my reference value there, when it goes positive, what happens? The output will go negative, all right? When it goes negative, that means there's 0 volts, it goes negative. How's the current going to flow? Current flow from positive to negative. That means, if I look at that Zener diode will be reverse biased, that Zener diode will be forward biased. That's why it's minus VZ1, minus 0.7 volts. When my input signal goes negative with respect to my reference, the output will go positive. There's 0, it will go positive. That means D2 will be reverse biased and D1 will be forward biased. That's why it's plus VZ2 plus 0.7 volts for that one. They call that a double bounded comparator. All right, up till now, we had a look at a comparator with nothing. Then we have a look at the comparator with the hysteresis. And now we look at the comparator with bounding. Now, example 13.3, they're going to compare this. They're going to give us a comparator with output bounding and with hysteresis. That is example 13.1. They say determine the output voltage waveform for figure 13.13. This comparator has both hysteresis and Zener bounding. The voltage drop across D1 and D2 are in either direction, 4.7 plus 0.7, that means 5.4. That means the one Zener diode will be reverse biased, the other Zener diode will be forward biased. That will give me 5.4 volt. Because one Zener diode is forward bias with a drop of 0.7, the other one is in breakdown. All right. You can see if we have a look at this circuit, there's my hysteresis and there's my output bounding. And there's my input signal plus 5, minus 5 volts. And that means I got hysteresis here, I got output bounding there. They say the voltage at the inverting of the op-amp Vout is plus minus 5.4. Since the differential voltage is neglectable, the voltage at the non-inverting and the inverting input op-amp must also be approximately plus minus 5.4. If you remember from chapter 12, that the op-amp always try to make this voltage difference equal to 0, because now there's feedback, it will always try to make that equal to 0. That's why I can say VR1 is Vout minus Vout plus minus 5.4, and that's equal to plus minus 5.4. I can work out IR1 is VR1 divided by R1. That means plus minus 5.4 divided by 100K will give me plus minus 54 microamps. Now they say, since the non-inverting input is input current is neglectable, I can assume the current flowing through R1 is equal to the current flowing through R2. That's why I can say IR2 is equal to IR1 is equal to plus minus 54 microamps. That means I can say VR2 is R2 times IR2, Ohm's law, and that will give me plus minus 2.54 volts. Then V out will be that volt drop plus that volt drop, those volt drops added, the plus minus 5.4 plus minus 2.54, that will give me plus minus 7.94. That means that will be my output voltage. The upper trigger point is going to be R2 over R1 plus R2 times the output voltage. That means the upper trigger point will be the positive one, and that will be 2.54 volts. The lower trigger point will be the same resistor values, but just minus V out, and that will give me minus 2.54 volts. All right, let's quickly have a look at the waveforms. My upper trigger point is 2.5 volts. My lower trigger point is minus 2.54 volts. The sine wave goes to plus 5, minus 5. That means at this point, my input voltage is negative with respect to my reference. All right, it's negative. But where is my reference? My reference is positive. That's why the output will be at plus 7.94 volts. But at that point, what happens? Input signal becomes more positive than the reference, then it will shoot down negative to minus 7.94 volts. Now I will have minus 7.94 volts here. It will stay there for that duration of time, but here my input signal becomes negative with respect to my voltage there. When it becomes negative, then it will shoot up positive and stay positive for that duration of time. That is now comparator with hysteresis and output bounding. All right, we're going to talk about comparator applications. The first circuit we're going to look at is an over temperature sensing circuit. That means this circuit will give you alarm if there's any over temperature. First of all, comparator, R3 and R4 give us a reference voltage. But let's assume this reference voltage at this point is 5 volts. And we got a thermistor with a negative temperature coefficient. All right, let's assume the adjustments in such a way that the voltage here is 4.5 volts. So that means I got 5 volts for my reference, and I got 4.5 volts here. That means that is negative with respect to my reference. When it's negative, the output will be negative, and the transistor will be off. Now let's assume the temperature increases. That means a negative temperature coefficient means the resistance will decrease. When this resistance decreases, the voltage at this point will start increasing. Let's assume this voltage increase to, let's say, just above 5 volts. When it goes above 5 volts, This will be more positive than my reference. The output of the op-amp will go positive. There will be a base emitter current and will cause a collector emitter current to flow. We'll switch the transistor, energize the coil of the relay, and set off an alarm. Change the contacts and set off alarm. What is the purpose of this diode? You will notice if the current is flowing, this diode, there will be positive there will be negative there. This diode will be reverse biased. All right. A reverse biased diode will indicate that there is no current flow through it. All right, there can be a small leakage current. But the moment this transistor turns off, the magnetic flux of this coil collapses, generate an EMF with the opposite polarity. That means then the polarity will be positive, negative, and that voltage can be fairly high, and it can damage my transistor. Now this is for protection. That means the current will now flow through the diode. The diode will short circuit that and will protect my transistor. That is the oversensing circuit. Now we're going to have a look at the analog to digital converter. That means an analog voltage converted to a digital signal. All right. One practical application, if you think about a digital multimeter, what does we do there? If we measure voltage with a digital multimeter, it's an analog voltage converted to a digital readout. All right. Now when we look at this circuit here, we got a reference voltage and we got 1, 2, 3, 4, 5, 6, 7, 8 resistors. To explain it to you, what I'm going to do, I'm going to make my reference voltage 8 volt. All right, that means there's going to be 1 volt across each of these resistors. That means the first one, if I measure there from there to there, there's going to be 1 volt. From there to there, there's going to be 2 volts. From there to there, there's going to be 3 volts, 4 volts, 5 volts, 6 volts, 7 volts, 8 volts. All right. But all these comparators, or these op-amp comparators, are connected. All the inverting inputs are connected from the resistors, and then we got our input analog signal connected to all the non-inverting inputs. All right, here we got a priority encoder. It will give me basically a binary output. Now let's assume I apply, let's say, let's apply 1.2 volts here at the input, 1.2 volts. That means I got 1 volt there, I apply 1.2 volts. Now 1.2 volts is more positive than 1 volt, all right? That means the output of this bottom comparator will be a high value. In this case, 1.2 volt is negative with respect to 2 volts. That means there will be a negative output, negative output, negative output, negative, negative of a low output. All right. That means that's how we determine it. Let's say, for example, I apply 4.5 volts at the input. All right. There's 1, 2, 3, 4. All right. That means what is 4.5 volts with respect to 4 volts? Is more positive. I will have a high output. This one will have a high output. That one will have a high output. That one will have a higher output. All those will have low outputs. That is the principle how this analog to digital converter is operating. Just compare it, priority encoder, and then I also got my enable pulses there. All right, here they show us, they say sampling of values on analog waveform for conversion to digital. If we look at this, there's my analog signal, that's a varying signal. Now if we have a look there, at that point, what happens there? I got a little bit higher than 3 volts, and there's my enable pulses. That means I got enable pulses, that's enable pulses. Now, if I go and have a look here, we're going to look at this first one, at enable pulse 1. All right, what do I have? I have D0 a 1, and I have D1 a 0, and D2 all a 0. That means a high state, and a low state. 2 to the power 0 is equal to 1, and 2 to the power 1 is equal to 2. That means what will I measure there? I will actually measure 3. We're going to have a look at that point there. Enable pulse number 4. Enable pulse number 4, what will I have? I will have low state, high state, high state. That means that will give me 2, and 2 to the power 2 will give me 4. That will give me, all right, that will be 2 to, that will give me 0. 2 to the power 1 will give me 2, and 2 to the power 2 will give me 4. That means that will give me 5. That's how that is operating. Specific comparators. We get specific comparators. That means you can go buy a op-amp that is a specific comparator, and that's, for example, a LM111, a LM211, or LM311. That is op-amps that is basically designed to act as comparators. And they got a lot of different features that the normal op-amp don't have. All right, here they show us 2 comparators, all right. First of all, here we see we got a reference voltage. We got a 100K and a 10K, and my voltage there is 15 volts. That means I will have a reference voltage. That means that input voltage will be compared with the reference voltage. That means the voltage across the 10K. In this case, I have a negative voltage. That means my reference voltage will be negative, and that will be actually the volt drop across the 22K will be my reference voltage, and my input voltage will be compared with that. That means I will compare this input voltage with a negative voltage. (30.2). We can also use op-amps as summing amplifiers. That means we can add up voltages. We can add voltages together, and now we're going to look at the summing amplifier with unity gain. That means the gain is going to be equal to 1. That means, well, that's why we call it the unity gain. That means R1, R2, and R3 will normally have exactly the same resistor values. That means if that's a 10K, that will be a 10K, and that will be a 10K if I look at the unity gain. Now, the easiest way, that means here I will have a current, there will have a current. That means that current added to that current will give me my total current, and if I take that total current, multiply by my feedback resistor, that will give me my output. But my output will be negative. If that is positive and that is positive, the output will be a negative voltage. And please remember, we got a very high input impedance. Nothing is flowing into the op-amp. That means those two currents added together will give me my total current, and I can determine my output. Or I can take that voltage and that voltage, add them together, and that should give me my output, and that will be just 180 degrees out of phase. That means it will be negative. Let's quickly have a look at the proof. Here they got a very small, simple proof. I total is equal to I1 plus I2. Just to show you again, there's I total, it's I1 plus I2. Because that point is at 0 volts, the op-amp will take its output negative to make sure that current is equal to the sum of those two currents. And they should flow in the same direction. Right, now we can say V out is equal to minus I total times RF. I repeat that minus indicates 180 degrees phase shift. Now I can say V out is equal to I1 plus I2 times RF, because that will be Ohm's law. But I1 is Vn1 divided by R1. I2 is Vn2 divided by R2 times RF. They say all three of the resistors are equal. R1 is equal to R2 is equal to RF is equal to R. Then that can cancel out. That cancel out. Then I can say V out is equal to minus V in plus V in 2. All right. Or we can state, if I got multiple inputs there, Vn1, Vn2, Vn3 up to Vn, that means my output is going to be equal to all those added, and the output will be negative with respect to my input. Let's have a look at example 13.2. Here you can see I got a unity gain, 10K, 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 10K. All of them are equal. 3 volts, 1 volt, 8 volt. That means 3 plus 1 will give me 4. 4 plus 8 will give me 12. That means the output voltage will be minus 12 volts. All right. That means we add those voltages together. All right, summing amplifier with a gain greater than unity. That means when I increase the resistance value of my feedback resistor, if you have a look here, I got a 1K, a 1K, and I got a 10K. That means I will actually have a gain here of 10. All right, that means the gain will be 10 because my feedback resistor is 10 times larger than my input. All right, here they give us the formula for that. They say VR is equal to minus RF over R times Vn1 plus Vn2 plus Vn. All right. Now let's have a look at the example. This example 13.6, they say determine the output voltage of the summing amplifier in figure 13.23. We have a look here. My input voltage Vn1 is 0.2 volts. Vn2 is equal to 0.5 volts. That means 0.2 plus 0.5 will give me 0.7. Multiply by 10 will give me 7. Inverting input minus 7 volts. There they show you. They work out the gain is going to be 10. And I got 0.2 volts and 0.5 volts. That means the output will be minus 7 volts. Now we can also get an averaging amplifier. You can also get an averaging amplifier. They say a summing amplifier can be made to produce a mathematical average of the input voltages. This is done by selecting the ratio of RF and R equal to the reciprocal of the number of inputs. That means if I got 2 inputs and I want the average, I divide by 2. If I got 4 inputs and I want the average, I divide by 4. That means that's the way we normally determine the average, and we can also do that with op-amp. If we look at example 13.7, they say show that the amplifier in figure 13.24 produce an output whose magnitude is the mathematical average of the input voltages. Now you see we got 4 input values here, and all these resistors are 100K. That means my feedback resistor must be 100K divided by 4, and that will give me basically 25K. They say since the input resistor 100K, the output voltage is Vout is RF divided by R times Vn1 plus Vn2 plus Vn3 plus Vn4. Now that will be 25 divided by 100. That means that will give me a quarter. Now if I add this up, 1, 6, 1 and 2 is 3, it's 6, it's 10. If I take 10 and I divide by 4, what should I get? I should get 2.5. That will give me the average of that. Can you just stop quickly? Ready? All right, scaling adder. That means in the case of a scaling adder, we're going to put certain weights to each input. That means all the inputs are not going to have the same value, and that is a scaling adder. That means the gain of each of the inputs is going to change. That's why they say VR is equal to minus RF over Rin times Vin1 plus RF over R2 times Vn2 plus RF over Rn times Vn. All right, let's have a look at the example. They say determine the weight of each of the voltage of the scaling adder in figure 13.25 and find the output voltage. Now when you look at this circuit, I want to point out R1 is a 47 kilo ohm, R2 is a 100 kilo ohm, and R3 is a 10 kilo ohm. Now you can see I got a feedback resistor of 10 kilo ohm. That means all these resistors got different values, and that means they got different weights. Now, if you have a look, they calculate the weight of input 1, 10K divided by 47 kilo ohm, and that give me 0,213. Weight of input 2 is 10K divided by 100K, and that will give me 0.1. And then the last one, input 3, is a 10K divided by 10K. That will give me a value of 1. All right. That means the lowest resistance will carry the highest weight. All right. Now let's go and work out the output. That is Vn1 multiplied by its weight. That means 0.213 times 3 volts. The second one of input 2 is going to be 0.1 times 2 volts. And the last one, input 3, Vn3, is going to be 1 times 8 volts. Now, when we work it out, we get a total of 8,84 volts negative. I repeat, 180 degrees phase shift because that's the inverting connection. Now we're going to look at, we had a look at analog to digital converters. Now we're going to look at the digital to analog converter. That means where I take a digital signal and convert it to an analog signal, and there we're going to make use of weights. We're going to look at the different weights. All right. All right, if we look at the first one, a scaling adder as a 4-digit to analog converter. That means we start here with 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. Now, 2 to the power 0 will give me 1. 2 to the power 1 will give me 2. That will give me 4, and that will give me 8. That means this one will carry the highest weight, and that one will carry the lowest weight. And if you have a look at the resistor values, that is R, that's 2R, 4R, and 8R, because that is a binary system. System of 2. That means each time it increases by a value of 2. If I take R and I multiply by 2, it will be 2R, 4R, and 8R. That means the least amount of weight, the highest weight. Right, let's have a look at this example. They say determine the output voltage of a digital analog converter in figure 13.27a. The sequence of the 4-digit binary codes represented by the waveform in figure 13.27b are applied to the inputs. A high-level binary 1 and a low-level binary 0. The least significant binary digit is D0. You see there's D0, and you can also see the highest resistance for D0 and the lowest resistance for D3, all right? And they indicate a low level as 0 and a high level as 5. You can see, you look at this figure here, you can see if I connect it to the positive voltage, it will indicate high levels. If I connect it to the 0 volts, it will indicate a low level. All right, here's my pulses for D0, for D1, for D2, for D3. Now they can also work out the currents. If I go and take 5 volts divided by 200K, because this point is at 0 volts, because the op-amp will always try to make the input voltage difference 0. That means now 5 volts divided by 200K will give me 0.25 milliamps. 5 volts divided by 100K will give me 0.5 milliamps. 5 volts divided by 50K will give me 0.1 milliamp. And 5 volts divided by 25 kilo ohm will give me 0.2 milliamps. Now you can see also it doubles. If I take 0.25 milliamps multiplied by 2, it will give me 0.5. I take 0.05, sorry, multiply by 2 will give me 0.1. If I take 0.1 multiplied by 2, it will give me 2 milliamps, all right? And then they work out the output voltages. That means it's the feedback resistor times the current. For D0, it will give me 0.25 volts, minus 0.25 volts. For D1, it'll give me minus 0.5 volts. For D2, it'll give me minus 1 volt. And for D3, it'll give me minus 2 volts. Now, for a system like this, if I look at the system like this, if we look at the system like this, d to the power 0 is 1. D to the power 1 will give me 2. D to the power 2 will give me 4. And D to the power 3 will give me 8. That means if I add all up here, it will actually give me a total count of 16. And that is called hexadecimal. And that brings us to the following. All right, there we got 0, that minus 2.5. That means we can get a total count of 16, and that's called hexadecimal. All right. That will give me 15, and 0, that means a total count of 16, and that will give me hexadecimal with from D0, D1, D2, and D3. The next circuit is a R2R ladder network, digital to analog converter. Now, the only thing I want from you to know, you must know the circuit diagram, and you must know which resistors are R and which resistors are 2R. That means we're only going to use 2 resistors, a 2R and an R. And very important to notice, if you have to select certain things, you can't leave these inputs open. That means if I want to select 0 for all of them, I must connect each one of these inputs to 0 volts, or to my reference. If I want to indicate, let's say I only want to have D1 a high state, then I connect that to a high value, and all those other ones must be connected to 0 volt. That's the only thing I want you to know. I don't want to do the next work on the next page. I'll show you why. Because it takes a lot of time, because you must go and draw the equivalent circuit for each one of those circuits if you want to work out the output voltage. You must draw each circuit, and you must get the equivalent circuit to determine the output voltage.